Okay, welcome. Today we are going to see about the transformer problems. This one is the first problem. The maximum flux density in the core is core of a 250 bar 3000 volt transformer. 50 hertz single phase transformer is 1.2 Weber per meter square. If the EMF per turn is 8 volt, determine primary and secondary turns area of the core. Okay, the given, what are given? You can see the maximum flux density is 1.2 Weber per meter square. So B max is equal to 1.2 Weber per meter square. Then the given is 250 volt bar 3000 volt transformer. So V1 and V2, the turns ratio, sorry, the voltage ratios are given. V1 is 250, V2 is 3000 volt. Frequency is 50 hertz. And the EMF per turn, okay, per turn induced EMF is 8 volts. It's also given. What you are going to find? Primary and secondary turns and area of the core. Okay, the solution you can see E1 is equal to N1 into EMF induced per turn. Okay, you know that E is equal to N into total number of EMF induced in it. Okay, I'll tell you. You can see E is equal to N into total number of flux linkage in it. Okay, di by dt. This is the previous formula. Okay, here this term di by dt is being converted into EMF induced per turn. Okay, so you can substitute whatever you are having. You need to find the number of primary turns. So N1 is equal to E1 into EMF induced per turn. So what you get is 250 divided by 8, which is 32. So if you know this one is 32, then you can find N2 also. How you can find N2? The turns, the per turn is given. Okay, 8 volt is being induced per turn. So N2 is equal to 3000 divided by 8. So you will get 375. Next, what you need to know is the area of the core. So to find the area of the core, you are having the formula. The total induced EMF in the secondary E2 is equal to 4.44 F N2 BMA. Okay, you can neglect this minus term. Okay, this minus term is not needed. Make it as plus, or you can just remove this term. Okay, you know E2 is 3000. From where you can know this one is the 3000, this is the V1 and this is V2. So it is E1, this is E2. Okay, so E2 is 3000, substitute here 4.44. Yeah, frequency is 50. N2 you have found 375. The maximum flux density is given, this is 1.2 Webers per meter square, substituted. Area is not given, so area. So you need to find the area of the core, just cross multiply all the values, you will get 0.03 meter square. That's all. This is the second problem. A single phase transformer has 400 primary and 1000 secondary turns. The net cross sectional area of the core is 60 centimeters square. If the primary winding be connected to a 50 hertz supply, 250 volt, sorry, supply to at a 520 volt, calculate the peak value of flux density in the core, the voltage induced in the secondary winding. So you are going to find peak value of flux density in the core as well as the voltage induced in the secondary winding. Okay, here the primary turns is 400 and the secondary turns is 1000. So N2 is 400 and N1 is, sorry, N1 is 400 because primary is N1. Okay, N1 is 400 and N2 represents secondary. So N2 is equal to 1000. The net cross sectional area of the core is 60 centimeters square. So A is equal to 60 centimeters square. If the primary winding be connected at a frequency which is 50 hertz, so F is equal to 50 hertz, and the voltage being supplied to the primary is 520 volt. So V1 is equal to 520. So you can directly write the peak value of flux density in the core. You are going to find this one. To find this one, you need to know the transformer ratio. So you can find the transformer ratio K is equal to N2 divided by N1. Put all the values, 1000 divided by 400, you will get 2.5. Okay, K is equal to 2.5. Next, you know the transformer ratio K is equal to E2 by E1. Okay, you can remember this formula. K is equal to N2 divided by N1 equal to V2 divided by V1, which is equal to I1 divided by I2. Okay, this is the formula to find the transformation ratio K. So you can say E2 is divided by E1 is also K. Here E2 and E1 are nothing but V2 by V1. Okay, so you can find E2 is equal to K into E1. You know K is equal to 2.5 and E1 is given, which is 520 volt over here. So substitute this thing, you will get E2 is 1300 volt. Next, we are going to find the flux density. Okay, what here? It's okay. Okay, I will tell you. Okay, the second one is this one. Okay, the second one, the voltage induced in the secondary winding. Okay, you have found it here. 1300 volt. This second step you have done in the first step. Okay, you can see this voltage induced in the secondary winding, which is nothing but E2. Okay, E2 or V2 equal to is 1300. You have done this thing in the first step. Next, in the second step, you are doing this first one. Okay, the peak value of the flux density in the core. For this, you know the formula. E1 is equal to 4.44 F N1 BMA. So all the values are given. Okay, you can substitute E1 is equal to 520, 4.44. F is frequency, which is nothing but 50 hertz. N1 is given, which is 400, and the maximum flux density is not known. Okay, and the area of the core is given. Where it is given? Here. You can see the cross sectional area of the core is 60 centimeter square. So 60 into 10 power minus 4 meter square. To convert centimeter square into meter square, you need to multiply 10 power minus 4. Okay, if you do so, you will get 60 into 10 power minus 4 meter square. So maximum flux density is Bm. So cross multiply all the values, you will get 0.976 Weber per meter square. A 25 kVA transformer has 500 turns on the primary and 50 turns on the secondary winding. The primary is connected to 3000 volt 50 hertz supply. Find the full load primary and the secondary currents, the secondary EMF, and the maximum flux density of the core. Neglect leakage drops and no load primary current. So, you know the power rating of the transformer is 25 kVA and the primary turns N1 is equal to 500 and N2 secondary turns is 50 and primary is connected. So this is V1. V1 is equal to 3000 volt and the frequency is 50 hertz. So what you're going to find? Full load primary and secondary current. You are going to find the currents and the present in the transformer. So I1 and I2. You are going to find I1 and I2. And the maximum flux in the core. Okay, you are going to find pi value, maximum flux in the core, and you should neglect the leakage drop and no load primary current. Okay, let us find. So from the turns ratio, this is N1 and N2, you can find the turns ratio K. Okay, K is equal to N2 divided by N1. You get 50 divided by 500 is 1 by 10. Okay, 1 by 10 is nothing but 0.1. Okay, now you can easily find I1. Okay, I1 is equal to okay, I is equal to what they have done here is I will tell you. You know, P is equal to V into I. Okay, we know this thing. Okay, V into I. Okay, what they have done here is they are finding I. I is equal to P divided by V. Okay, so we are finding I1. Okay, so now you can see the power. Here you have said power is 25 kVA. So 25,000 and the voltage across the primary is given. What is it is? 3000 volt over here. Okay. So 25,000 divided by 3000 give you 8.33 ampere, which is nothing but I1, the total current in the primary. To find the secondary current, you can use the transformation formula. Okay, K is equal to I1 by I2. So I2 is equal to I1 divided by K. Okay, so you can apply this formula. K is equal to 1 by 10. So 10 into 8.33 is coming. Okay, so you get 83.3 amperes in the primary. Next, you know, EMF per turn on primary side is 3000 divided by 500, which is nothing but 6 volt. Next, the secondary EMF is nothing but the turns, that is the primary turn side. We will get a 6 volt. Okay, so 6 into 50. Okay, to if you there are 50 turns. Okay, the total voltage coming here is 6 volt. So 6 into 50 will give you 300 volt. Similarly, you can find the E2 value by using the transformation formula. E2 by E1 is equal to K. So E2 will be cross multiplied. So E2 is equal to K into E1. So you know K is 1 by 10 and E1 is nothing but 3000. Here is 3000. Okay, 3000 and you will get 300 volt. Then you can find the flux. What they are asking here is find the full load primary and secondary current and then the secondary EMF and the maximum flux in the core. They are asking maximum flux in the core. So to find this, you know the same formula is E1 is equal to 4.44 F N1 pi M. Okay, here the pi M is not known. Other things are known. So substitute the values. E1 is nothing but the primary, which is 3000 volt. Substitute directly equal to 4.44. F is the frequency, which is 50. And N1 is nothing but the turns ratio. Primary one is 500. And pi m is not known. So you can cross multiply it and you can find pi m is equal to 27 milliwebers. And this one is the last problem. A single phase transformer has 500 turns in the primary and 1200 turns in the secondary. The cross-sectional area of the core is 80 square centimeters. If the primary winding is connected to a 50 Hz supply at 500 volt, calculate peak flux density and voltage induced in the secondary. So, you know the turns ratio. The single phase transformer has a primary is 500 and secondary it is 1200. The cross sectional area is 80 square centimeters and in the primary winding is connected to a 50 hertz supply. So the frequency is 50 hertz and the voltage is being the primary voltage is being 500 volt. You need to find the peak flux density, that is Bm, and the voltage induced in the secondary, which is V2. Okay, you need to find these two things. To find these things, there is a simple formula. Okay, E1 is equal to 4.44 F pi M into V1. Okay, substitute all the values. 500 is nothing but the E1 value. 4.44 frequency is 50. You don't know pi M, and the transformation ratio is N1. Here it is 500. Substitute it. Now you can know cross multiply pi m is equal to 1 divided by 222 Webers. Okay, just leave as it is, or you can simplify it and paste it, present it here. Okay. Next, you need to find the peak flux density. Okay, to find the flux density, you know Bm is equal to pi m divided by area. Okay, the formula here is density Bm is equal to maximum flux divided by area. Okay, the area is cross sectional area. So you have find pi m is equal to 1 by 222, substitute, and you know this area. Okay, area is given here. The cross sectional area of the core is 80 square centimeter. To convert centimeter square into meter square, I tell you, you should multiply by 10 power minus 4. So just to do this, you will get the peak flux density Bm. It will be equivalent to 0.563 Weber per meter square. Next, you need to find the voltage induced in the secondary. So to find it, you know V2 by V1 is equal to N2 by N1 is equal to K. So you know all these values except V2. So you can say V2 is equal to N2 divided by N1 into V1. So just substitute all the values. Here V1 is 500, N2 is 1200, and N1 is again 500. You will get the secondary voltage V2 is 1200 volt. Thank you.